Chapter 6, Section 3. So keep talking about the definite integral and then area under a graph. Remember, a graph comes from a function, right? If it's a function, we can always graph it. So remember definite integral, which means this elongated integral has a lower limit, has an upper limit. Then this value is a two-dimension value, right? Because this and this makes a pair. This means cutting x-axis into infinitely many pieces. Then f of x is another dimension. Right? So let's say this is f of x. Right? Y-axis of the some way. So when we see definite integral, that means we have an interval. X value is a, x value is b. This is just an example, right? A and b doesn't really have to be here. It can be on the negative side of x. Then, so I have this definite integral. Remember from previous section, once we finish everything, this is a real value. It's a real number. So this real number represents the area of this function under this function, under the graph of this function with x-axis. So that's what this title means. So yeah, this is a beautiful picture. So I have this graph, f of x is the blue colored. The blue color is a graph of a function. And then we have lower limit a, we have upper limit b. So the area shaded will be the integration, lower limit a, upper limit b, f of x dx. Okay. So that's this. That represents the area of this. So let's see this one. So we can find the area under this using integrals that we wouldn't be able to do in algebra. So what do? We set up the integration. Goes from 0 to 1. Lower limit will be 0. Upper limit will be 1. So this is our x-axis. We're cutting x-axis from 0 to 1, infinite many pieces. Then the integrand, the inside here is called integrand, is this f of x. So x squared. X squared. So what do? How do we evaluate this? First, we anti-differentiate x squared by doing add 1 to the exponent divided by the new exponent. Then because it's a definite integral, we do not need to add c. If we do not have lower limit, upper limit, we would add c. We get a family of functions, really depends on c. If a given initial value or given 1 point, then we can get the value of c. But in this case, with definite integrals, we just want to evaluate x equals 0, x equals 1, and subtract them. So we get 1/3 of x cubed, right? Because x raised by 2 plus 1, x cubed, 2 plus 1 is 1/3. Then we evaluate at 1. So evaluate at 1, 1 raised by 3 is still 1, so we get 1/3. Evaluate at 0, we get nothing, so this is 1/3. So we don't carry, so this is pure mathematics. So no unit involved. So the area of this from 0 to 1 formed with x square function and x-axis is 1/3. So what we did is this, right? So this lowercase f is capital function f's derivative. So we anti-differentiate, we get f of x. Then we evaluate at the upper limit Then we evaluate it at the lower limit, then we subtract them. So this is doing one example. The function is a constant function. Right? So the function just f equals to 4. F equals 4. Let's draw the picture. So we have x-axis, we have y-axis, the same as f of x, and this is the same as f of x. Then let's see, this is the value of 4. So f of x equals 4, it's just this horizontal line, constant function. So what is the area from 0 to 3? This is 0. Let's see, this is a 3. We want to find the area of this. And of course, we can go through algebra, right? Algebra is 3 minus 0, so this will get a width 3, and this is a 4. 3 times 4, that should be 12. Well, let's go through doing integrals. So set up integral, going lower limit 0, upper limit 3, dx. Then the function just 4, constant function. So we anti-differentiate, we get 4x. Then we evaluate at 0, at 3. Then we subtract them. Yes, of course, we have to get the same answer as 12. Well, let's see this example. Right, this is given the function as a linear function. So going from 2 to 3. So we set up the integration, lower limit 2, upper limit 3. The integrand is a function given negative x plus 4 dx. So first, we anti-differentiate. So negative x, we add 1 to the exponent, we divide by 1 plus 1. And then 4 just 4x. So simplify, we get a negative half x squared plus 4x. Then we evaluate at 3, add 2, subtract them. In the end, we get 3 over 2. So figure 2c, let's see 2c. So 2c, we have to split it into, oh, it's in previous chapter. So sometimes we have split into two. Well, let's see, let's give an example. I think this one, see. Okay, so this, I can graph this. So from 0 to 2 is just identity function. From 2 to 4 is constant function. So the graph looks like this. From 0 to 2, so let's say this is a 2. From 0, let's see, this is a 2. From 0 to 2 is this identity function, right? X value and Y value are the same. And from 2 to 4, let's see, this is 4. This is a constant function too. So this is our function. So how do we find the area of this? Because we have two functions, right? We have this is an x function, this is a constant function. So we need to split into two. Of course, we can find by doing algebra. Right? If we do algebra, let's see what we get. We get, well, this is 2 times 2, 4, half over 4 should be 2, right? Or 2 minus this one, and times 2, 4 divided by half. So this part, area will be 2, and this part, 4 minus 2, which is a 2, 2 times 4, which is 8. So 4 plus 8. Excuse me. So 4 plus 8 should be 10. Right? why I wrote 4 here? That's, right, the function is, no, the function is 2, not 4. Okay, this is a mistake. The function is 2. The constant function is 2. Right? So 2 times 4, but this 4 minus 2, so this width is 2. 2 times 2, that's 4. So 2 plus 4, that's 6. So this is going through algebra. But we can do integration. So do integration from 0 to 2, we set this integral, right? Because the function is x. Then from 2 to 4, the function is 2. So the integrand is 2. Then we anti-differentiate, we evaluate. Anti-differentiate x, we get a half of x squared. Anti-differentiate 2, we get 2x. Then we evaluate. Half of x squared at 2, well, that's just 2. Right? Because 2 squared is 4, 4 times half, that's 2. Then 0 is nothing. Then 2x, 2 times 4, that's 8. Minus 2 times 2, that's 4. So we also get 6. Okay, this one we already did, so 1/3. Well, let's see this one. We want to find the area under the graph from -1 to 1. So all this shaded region. All this shaded region. So what do? We set up, so the function is given as such. 3x squared plus e to the x. That's going to be our integrand. So we're going to do lower limit is -1. Lower limit is always the left one on the integral because it's a lower limit, it's a less value. Upper limit is 1. 1 is always the one on the right. From -1 to 1, we have this function as the integrand at dx. So how do we do the calculation? Well, I don't need this anymore. So we're going to anti-differentiate. We anti-differentiate 3x squared. If we do, that's x cubed, right? Because we add 1 to 2, that's 3, divided by 3. So that's x cubed. Then plus e to the x. Well, derivative of e to the x is e to the x. Then we want to evaluate at the -1 and at 1. So at 1, we get a 1 raised by 3. Of course, it's 1. Then e to the 1, that's e. Then minus x raised by 3, -1 raised by 3 will be -1. Then plus e to the -1. So 1 plus minus 1 become +1, we have 2. So 2 plus e minus 1 over e. Okay, usually we take this one. If it's not application, we just take this pure mathematics solution. So 2 plus e minus 1 over e. Well, if it's application, well, we really want to find the area of this, so we can go to the calculator. So it's approximately 4.35. Let's see this one. So the function is given as polynomial degree 3. We want to find area in between 0 and 1. So we set up integral. Lower limit is 0, upper limit is 1. The integrand is x cubed plus 2x plus 1 dx. So setting up. Now anti-differentiate. So get x raised by 4 divided by 4 plus x squared, because 2x is the derivative of x squared plus 1x. Then evaluate is 0, evaluate at 1. Well, evaluation at 0 gets nothing. Evaluation at 1, we just get 1/4 plus 1 plus 1. Right? Well, 1/4 is 0.25, so get a 2.25. So that's the area of this shaded region. Okay, now we're going backwards, talking about Riemann sum. So how did we get the area under this? The underneath is Riemann sum. So we can split from A to B, we can split into two equal parts, right? So from here to here, from here to here, right? So this will be B minus A divided by 2, this middle one. We can split into 4, we can split into 4, so we split into 2, we split into 4, we split into 10, and this is we split into infinity. Right, we use the idea, we take the limit, we let n runs to infinity. So this is approximation, this is approximation, this is so this approximation is better than this approximation is better than this, but this is accurate. This is accurate, this is exact. So that's Riemann sum. Riemann sum is saying we're going to use rectangles to approximate the area under the curve, right? So this we can split into 2 parts, we split into 4 parts, we split into 10, we split into 100. This thing was split into infinite many. So using the limit idea. So now you see how beautifully these 3 things are tied together, right? This course is all about limits, differentiation, and integration. Differentiation, integration, or integration comes from anti-differentiation. Right? So these are 3 basics for calculus class. Let's see this one, this example. This example is saying to estimate the area of 100 foot wide. So from here to here is 100. Waterfront lot, a surveyor measured the distance from the road to the water line at a 20-foot interval. 20-foot interval, starting 10 feet from one corner of the lot. Use the data to construct a Riemann sum approximation. So that's the picture of it. So we're going to use Riemann sum to approximate. So each one equals to 20, right? You could see from this picture. Starting from this 10 to 30, that's 20, 30 to 50, that's 20, that's 20, that's 20, that's 10. So we want to do 20 multiplied by the height. And the height, sometimes we take the middle one, sometimes we take the left one, sometimes we take the right one. So it's just approximation. So in this case, it takes the middle one. You see this one? Let x1 be 10, x5 be 90. Then evaluate f of 10, f of 90. So the middle one. So f of 10 is this one. Right? F of 20. F of 10 is this. F of 10. F of 30. F of 50. F of 70. F of 90. Right? Then use 20 multiplied by this, 20 multiply, 20 multiply. So we get an approximation. That's called a Riemann sum. This one is divided into 4 parts. Right? So n equals to 4. So from 0 to 1. Well, 1 divided by 4 is 0.25. So each width of the rectangle is 0.25. Then we need to evaluate the function value, the height. So take the right one as x1. So we want to evaluate f of 0.25, f of 0.5. Then this we just add them together. F of 0.75, f of 1. So this is right. Then multiply by the width 0.25. So I have 4 rectangles. Right? We add the areas 4 rectangles to get a approximation of the area. So that's for this one. So roughly is 0.46875. Right, it's x squared. But remember what do we get? We get a 1/3, right? 0.333 something. So this is approximation, but the exact value is 1/3 we have done before. So this is the increase the partition by 10, right? That did 4. If we partition by 4, we get a 0.46. If we partition by 10, which means we cut into 10 pieces, then we get closer, get a 0.385. You can imagine if we do 100, even closer. But we don't have to do that anymore because we have the integration. We know how to find the exact value by doing so. By anti-differentiate the function, then evaluate at the upper limit, evaluate at the lower limit, subtract them. And that's called fundamental theorem of calculus. Fundamental theorem of calculus has 2 parts. So this is part 1. So this one. So this is a very important formula, maybe worth of noting. So this is fundamental theorem of calculus. This is just one part of it. So which means when we integrate a definite integral with a lower limit, upper limit, that just equals to anti-differentiation, antiderivative of the integrand, then evaluate at the upper limit, evaluate at lower limit, subtract them. And where does this come from? This comes from this. We take a limit, we let the partition runs to infinity. So the approximation becomes accurate. But this beautiful limit idea. Okay, that's a section 3, talking about exactly how to do definite integrals and find the area under a curve.